Hello, everybody. So far we introduced DFAs, introduced regular languages, and we try to prove closure properties on regular languages. In the process, we define this notion of non-deterministic finite automata, which is not exactly a computational model because you need to do things like guessing that we don't exactly know how to think of as computation, but we thought about it as verified guessing. Still, we were able to show that the languages that DFAs and NFAs recognize are the same. We did it through this subset construction that turned an NFA to a DFA that is equivalent. We didn't prove that they are equivalent, that they recognize the same language, but the proof is pretty easy. The construction really um, uh, in a very straightforward does it, and we can do it, the proof as usual by induction, that they recognize the same set of strings. Now we can go back to the closure properties that we got stuck on, and that's the reason we introduced NFAs, and complete them. And in the next video, we'll show that these closure properties are not just nice properties of regular languages, but in fact that we can define regular languages through these closure properties. So these closure properties actually characterize characterize regular languages. But let's take our time and first complete the closure properties. There'll still be interesting things here about how to use NFAs. So what we did before, what we completed is the union, the intersection, and the complement theorems. And we got stuck on the reverse theorem for regular languages. We wanted to say that the reverse of a regular language is also regular language. And the reverse of the language is just taking all the words in the language and reversing them, looking at them not from left to right, but from right to left. So a different way of saying it is that if a language can be recognized by a DFA that reads strings in the opposite direction from right to left, then there is also a normal DFA that accepts the same language, meaning that it accepts strings from left to right. And the proof now with the machinery that we have is not very difficult. Given a DFA for the language L, you can reverse its arrows, flip its start and accept states, and this will give you an NFA. It's not hard to prove that this NFA accepts exactly the right language, exactly the reverse language. But now we know that NFAs and DFAs are equivalent, so we can convert the NFA back to a DFA and get the DFA for the reverse language. So that's essentially the proof of the reverse theorem for regular languages. And something to note is that, and we saw an example where an NFA can be much simpler than the corresponding DFA for the same language. And therefore, using NFAs and knowing that they're equivalent could help us prove things about regular languages in a much easier way. That's something that's useful to remember for the homeworks and the quizzes. So for example, let's revisit the union theorem for NFAs. You want the union of these two DFAs, and previously we combined them to a DFA that runs in parallel on both of them. How would we do it here? How can we combine them to a DFA that computes the union? I'll ask you several questions this video, so it makes sense to freeze the video whenever I'm asking a question and trying to answer it yourself. So how would you do that? Well, one trivial way of doing it is just to draw a box around it and call it an NFA. So recall that NFAs can have more than one start vertex. And so you can guess if the word is accepted by this DFA or the other DFA. And once you choose correctly, you can run your computation on the right DFA. So this is a reduction. The reduction essentially takes the union of these two DFAs. Let's look now at, so we're left with two closure properties to prove, and we'll spend the rest of the video proving them. Regular languages are closed under concatenation. So the concatenation of A and B is all the strings that can be broken to V concatenated with W, such that V is in A and W is in B. So alternatively, you can take any pair of strings from A and B, concatenate them, and you get a string in the concatenation of A times B. And the only thing we know about A and B are that they are regular, and the only thing this means is there is a DFA M1 and M2 such that M1 recognizes A, M2 recognizes B, and somehow we want to create one that recognizes the concatenation of A and B. And the idea is that you run the computation first on M1, and from every accept state in M1, you can move to the start state of M2. So you're going to connect accept states to start states. And this will allow you now to move to the second part of the computation where you're supposed to guess you can supposed to verify that W is in B. And the guessing part is going to be guessing when does V end and when does W begin. So when to kind of jump from M1 to M2. We could have proven it directly with DFAs, but the proof with an NFA is just much, much simpler. So let's give an example of how to concatenate two DFAs, how to concatenate their languages that they recognize, and we'll do it for simplicity with the same DFA. So how to concatenate the language recognized by this DFA with itself. So we take this and we split it. We'll see this. And now we need to connect them. So what we said, we're going to connect accept states from the first one to start state in the second one. How do we connect them? We connect them with epsilon transitions. We connect them with epsilon transition, and that's something that you can take. So whenever you are in an accept state of the first DFA, you can decide that V ended and jump to the start state of B of the second DFA to see that that W is also in B. So that's almost done. What else should we do? Well, we should turn the accept states here to regular states, because otherwise we will also be accepting A. Right, so these are no longer, you cannot accept just by staying in M1. You need to do a calculation in M1, reach a former accept state, and jump to the start state of M2 and do the calculation. So that's essentially how you prove the concatenation theorem for regular languages. And we'll now move to the right, and the language that you recognize is the concatenation of the two languages. The proof is not very hard, and we'll see actually a more complicated version of this proof soon. So the clean star, in some sense, is a more a stronger version of the concatenation theorem, apart from the fact that it only concatenates A to itself. So A star is all the words that can be viewed as a concatenation of S1 up to Sk, so broken to S1 till Sk, where K is larger or equal 0, and each Si is in A. Now, again, I'm reminding you that K can be 0, in which case the empty string is going to be it's the only string that you get from concatenating 0 strings. And therefore, the empty string is always in A star. So again, what we know about A is that it has a DFA, that M that recognizes it. So M is this DFA, and L is the language recognized by M. And now we want to construct an NFAN that recognizes L star. So this is the DFA, and now how would we do that? So I let you think about it, and it is related to the concatenation. So just like in the concatenation, we're going to have epsilon transitions from accept states to the start state. So you can do a calculation, and whenever you're in accept state, you can say, okay, now I've seen so far what I've seen, I call it S1, and I'm jumping to the start state, and I'm starting a calculation that will reveal to me S2 and show that S2 is in L of N. That's almost correct. That's not perfect. What's missing? What's missing is that we also need to accept the empty string. And in this example, when the start vertex is not accept, then the empty string will not be accepted by this. So that's not difficult. We have a start state, a new start state, which is an accept state, and an epsilon transition to the original start state. So that's the entire construction. And this time we will try to give a proof that the language that this construction recognizes is exactly L star. So we'll give a sketch of this proof. It's a little bit detailed. Usually when we do that, there will be two sides, and one of them will be easier because one of them we constructed exactly, we made the construction exactly for this side to work. So this construction is made to show that everything in L star can be computed by this NFA. And the one that will be more challenging is to show that with this construction, we're not recognizing, not accepting strings that are not in L star. So let's do the two parts. Right, so we have the construction, and before we prove, we need to formalize the construction. So we have a DFA-M, and we're going to output an NFA-N, and ideally, and why can we start with a DFA rather than an NFA and still end with an NFA? It's because DFAs are equivalent to NFAs. That's what we've proven. So as an input, we're going to take something that's easiest to work with, which is DFA. But as an output, we let our algorithm have the freedom of constructing NFAs. Now, because it's equivalent, we can do that. So let's formalize the construction. Q prime, the new states is exactly the old states, plus this new start vertex, Q0, which is going to be the new start vertex. And that's the one that allows us, as we said, to accept the empty string. What about the accept strings? The accept states are going to be exactly the accept states from before, but also this new state, new start vertex, that its own purpose was to accept the empty string, so it has to be an accept state. Now let's talk about the transition. The transition from Q and A is as follows. If Q is an original state, and the transition is on any alphabet symbol that is not empty, then we're just going to do the transition we had before. So previous transitions are going to be kept. If Q is an accept state, we are going to add epsilon transitions, right, to the start vertex. So if Q is accept state and A is epsilon, then we are moving to the start vertex of the DFA of M. If Q is this new start vertex, then the only transition we allowed is the empty transition, which will take us to the start vertex of the original DFA. If Q is the new start vertex and A is anything else, then we have no transition defined. And for everything else, we have no transition defined. So the transition is to the empty set. So that's exactly the one, it's formalizing exactly the one from the picture in the previous slide. So if it confuses you, go back to the previous slide and kind of do matching and see this part of the definition matches the other part. And notice that the alphabet didn't change and the new start vertex is Q0. So let's look at this proof that regular languages are closed under the star. And this says that we need to prove that L of this new non-deterministic finite automata N equals L star. And as I said, this contains two parts. We need to show that L of N includes L star. And this is the part that's going to be easier because that's how we constructed things. We constructed things to be able to accept all of the things in L star. And again, for any proof that you'll have of this sort, when you're doing some kind of a reduction, often one side will be easier and you need to make sure that the other side also holds. The other side is that L of N is contained in L star. So that this construction didn't give you additional strings that you accept that you shouldn't accept. So let's do the easier part first. Assume you have a string W in L star. Meaning is that you can divide it to the concatenation of W1 up to WK, where each one of them is in L. This is what being in L star means. And now we'll prove it. How would we prove it? Yes, we'll prove it by induction, and induction on K, on the number of strings you're going to recognize. What are the base cases? Or it was enough to have one, but let's do two. The first best case is when k equals 0. When k equals 0, then we're talking about the empty string. And we made this construction such that the empty string is accepted because um, the start vertex is an accept vertex. So whenever the start vertex is an accept vertex, the empty string is accepted. For k equals 1, we just have w, which is in L. And this is again going to be accepted because we can have the epsilon transition from the new start vertex Q0 to Q1, which is the original start vertex. And now we can do the computation just as in the DFA. We're not taking any more epsilon transitions. And since W is in L, we're going to accept it. So that's 2 is easy. And let's do the inductive step. So assume that n accepts all strings, v, which is v1 concatenated with v2 up to vk in L star. So each vi is in L. And now we want to show that you also accept strings that are the concatenation of k plus 1 elements in L. So u1 up to uk plus 1. And so since n accepts u1 up to uk by induction, then what do we know? We know that we can reach in n, when walking on u1 up to uk, we can reach an accept state. And what we can also recall is that from every accept state, there is an epsilon transition to the start vertex Q1. Therefore, we know that after reading U1 up to UK, we can be in the start vertex Q1 of M. Now, we also know that M is going to accept UK plus 1, meaning that now when we run the computation on UK plus 1, at the end, we are going to reach an accept state of M. So all of this together means that N can also accept U. It has a path that leads to acceptance, a path where we're starting with accepting U1 up to UK, taking an epsilon transition to the start vertex and accepting UK plus 1 in M. So by construction, we see that N accepts U. And this can be written more formally, of course, but it's not difficult. So let's do the more difficult side, which is to say that L of n is contained in L star. So assume that W is accepted by n. What we want to say is that W is contained in L star. And this means is that we can break W to substrings that W is their concatenation, and each one of the substrings is accepted by, is in L. If W is the empty string, then W has to be in L star. So the clean star contains every contains the empty string for every L. So we're going to prove this again by induction. And the induction here will be slightly more interesting. It will be on the number of epsilon transitions we are taking. So n accepts U. And let's say that there is an accepting path of U that takes at most k epsilon transitions. So we're going to do an induction on the number of these on k. So the induction hypothesis is going to be that whenever n accepts u with at most k epsilon transitions, then u is in L star. Now, what about the induction hypothesis? Well, the only string by construction that can be accepted with 1 epsilon transitions, sorry, 0 epsilon transitions is the empty string. And since the empty string is in L star, then the base of the induction hypothesis holds. So assume that W is accepted by N with K plus 1 epsilon transitions. So we made the induction hypothesis for everything that can be accepted with K epsilon transitions. And now let's look at K plus 1 epsilon transitions. So here is the entire computational path. We know that the first edge you're taking, if you're taking any edge, is an epsilon transition because the start vertex is only connected to another vertex by an epsilon transition. So so we have a computational path. The computational path is just one of these paths in these trees. And we know that this path has K plus 1 epsilon transitions. And we're going to divide W. So we're accepting W with K plus 1 epsilon transitions. We're going to divide it to the concatenation of two strings, U and V, where V is a substring that we read after the last epsilon transition. So let's say that this is the last epsilon transition. In the path to this epsilon transition, we read U, and in the path after, we read V, and we reach an accept state. So this is U, and this is V. U is in L of N. Why is it true? It's true because epsilon transitions are only from accept states. In the construction, the only epsilon transitions are in accept states. So before taking this epsilon transition, we read U entirely, and we reached an accept state of N. Therefore, U is in L of N. And now, by the induction hypothesis, we can say that U is in L star, because we accepted U with K epsilon transitions. V, on the other hand, is in L. Why is it correct? Because epsilon transitions always reach Q1, the start vertex of M, and a computation that starts from Q1 and reaches an accept state without taking any epsilon transition is a computation that is entirely within M, within the original DFA, and it is an accepting computation within the DFA. So V has to be in L. And therefore W, which is U concatenated with V, is in L star. So that's a slightly more subtle proof, and you can stare at it, rewind me again and again if you can stand it, and convince yourself that that's correct. So with this, we completed all the closure properties that we wanted: the union, intersection, complement, reverse, concatenation, and the star, which we just proved now. And in the next video, we're going to look at the power of these closure properties. Thank you.